a star that has been shining since nearly the dawn of time, a planet-sized diamond orbiting a pulsar, or a star so cold it resembles a failed planet. Now imagine a cosmic riddle, stars that dim unpredictably or defy the laws of physics by existing at all. These aren't science fiction, they're the universe's most bizarre realities, each one rewriting the rules of astrophysics. Welcome to Infinitia Verity, where we explore the infinite mysteries of our universe. In today's episode, we'll uncover the strangest stars in the cosmos. Stars so weird, they challenge our understanding of how the universe works. Let's dive into the mind-bending world of impossible stars. The discovery of SDSS J102915 plus 172927 was a watershed moment in astronomy. Located in the constellation Leo, this faint star challenges everything we know about stellar formation. Found in 2011 using the European Southern Observatory's Very Large Telescope, SDSS J102915 plus 172927 is one of the purest stars ever observed. This star contains almost no elements heavier than helium, what astronomers call metals. Metals are crucial for star formation, acting as cooling agents that allow interstellar gas clouds to collapse under gravity. Without them, conventional theory states that stars can't form. And yet, SDSS J102915 plus 172927 exists, forcing scientists to rethink the early universe's conditions. A window into the early universe. SDSS J102915 plus 172927 is over 13 billion years old, making it one of the first stars formed after the Big Bang. Back then, the universe was a very different place. Heavy elements didn't yet exist. The cosmos consisted almost entirely of hydrogen and helium, with trace amounts of lithium. This star belongs to the second generation of stars, known as Population 2 stars. These stars formed after the first massive metal-free stars, Population 3, went supernova, scattering heavy elements into space. However, SDSS J102915 plus 172927's composition suggests it formed in a region that somehow remained untouched by this enrichment process. Why it shouldn't exist. The metallicity of SDSS J102915 plus 172927 is astonishingly low, just 0.00007%, or about 5,000 times less than the Sun's metallicity. For a long time, astronomers believed stars with such low metallicity could only form as massive giants which burn out quickly. Yet SDSS J102915 plus 172927 is a small, low-mass star with only 0.8 times the Sun's mass. Its survival for over 13 billion years makes it a cosmic time capsule, offering a glimpse into the universe's infancy. Impact on astrophysics. The existence of this star has profound implications. It suggests that under certain conditions, low metallicity stars could form even when theory says they shouldn't. This discovery has spurred searches for more stars like it, known as ultra-metal-poor stars, to better understand the processes that shaped the early universe. Interesting facts. If you compress the universe's 13.8 billion-year history into 1 year, SDSS J102915 plus 172927 would have formed in early January, while our Sun wouldn't appear until September. Its light has traveled across the universe for over 13 billion years, meaning observing it is like looking back in time to when galaxies were just beginning to form. Stars often create exotic companions, but few are as extraordinary as the diamond planet orbiting PSR J1719-1,438. Discovered in 2011, this pulsar and its glittering partner lie 4,000 light-years away in the constellation Serpens. A pulsar's deadly origins, PSR J1719-1,438 is a pulsar, a type of neutron star that forms after a massive star goes supernova. Pulsars are incredibly dense, just a few kilometers in diameter, but pack more mass than the Sun. They rotate rapidly, emitting beams of electromagnetic radiation that sweep across the cosmos like cosmic lighthouses. PSR J1719-1,438 spins at over 10,000 revolutions per minute, making it one of the fastest spinning pulsars ever observed. The birth of a diamond. The diamond planet likely started as a white dwarf, a dead star that lost its outer layers. Over millions of years, the pulsar's immense gravity siphoned away the white dwarf's material, leaving behind a core of carbon and oxygen. Intense pressure and heat compressed this core into a crystalline structure, forming a planet-sized diamond. This glittering world is about the size of Jupiter but much denser. It orbits PSR J 1719-1438 so closely that a year on the diamond planet lasts just 2.2 hours. How bright is it? While the planet's surface is likely dark and non-reflective, its crystalline structure means it could faintly sparkle in infrared light. However, from Earth, it's too far away to see directly. Interesting facts. A cubic centimeter of the diamond planet would weigh about 2 tons on Earth. If placed in our solar system, the diamond planet would outshine every jewel on Earth combined, though it wouldn't be visible to the naked eye. Tabby's star, officially known as KIC 8462852, burst into the public eye in 2015 after researchers noticed its bizarre dimming behavior. Unlike typical stars, whose brightness varies predictably, Tabby's star dims sporadically and without warning, losing up to 22% of its light. Alien megastructures or something else? The star's erratic dimming led some to speculate about alien megastructures such as Dyson spheres, hypothetical structures built by advanced civilizations to harvest a star's energy. While intriguing, this idea has no supporting evidence, and scientists have proposed more plausible explanations. Comet swarms and dust clouds. One theory suggests that a swarm of comets orbits the star, periodically blocking its light. Another possibility is a massive dust cloud orbiting at an irregular distance, causing uneven dimming. However, neither explanation fully accounts for the star's behavior. Interesting facts. Tabby's star sparked one of the first crowd-funded astronomy projects, with over $100,000 raised to fund additional telescope time. Its dimming has no fixed pattern, making it one of the most enigmatic stars ever studied. The search continues. Despite years of observation, Tabby's star remains a mystery. Its unpredictable behavior challenges our understanding of how stars interact with their environments. Quark stars are theoretical objects that lie at the boundary between the known and the unknown. They are believed to form when neutron stars, already among the densest objects in the universe, collapse even further. What are quark stars? Neutron stars are born in the violent aftermath of supernovae, when the core of a massive star collapses under its own gravity. In these stellar remnants, the matter is packed so tightly that protons and electrons combine to form neutrons. Quark stars, however, take this process one step further. If a neutron star's core becomes sufficiently dense, the neutrons themselves break apart into their constituent particles, quarks. This creates a new state of matter known as quark matter, denser than anything else in the universe. Quark stars are purely theoretical. No definitive evidence of their existence has been found. However, they could help bridge the gap between nuclear physics and quantum mechanics, offering a glimpse into the behavior of matter under extreme conditions. How are they formed? The formation of a quark star would require pressures and densities even greater than those found in neutron stars. This might occur during the collision of two neutron stars, an event that also produces gravitational waves. Scientists believe these events could briefly create quark gluon plasma, a substance resembling the state of the universe just moments after the Big Bang. If a quark star forms and stabilizes, it could remain in this exotic state for millions of years. Strange quarks and strange matter. Some models suggest that quark stars might contain strange quarks, a type of particle that doesn't exist in normal matter. If strange quarks dominate, the star could be composed of strange matter, a theoretical substance so stable that it could convert any normal matter it touches into more strange matter. This has led to a fascinating and slightly terrifying idea. Quark stars could act as cosmic contagions, spreading strange matter throughout the universe. What would a quark star look like? Quark stars would likely resemble neutron stars, but with subtle differences. They might emit bursts of gamma rays or X-rays due to their unique internal structure. Some scientists have suggested that certain gamma-ray repeaters observed in deep space could be quark stars in disguise. Why quark stars matter? If quark stars exist, they would represent an entirely new class of astronomical objects. They could provide insights into the fundamental building blocks of matter and the forces that govern their interactions. Interesting facts. A sugar cube-sized piece of quark star material would weigh as much as Mount Everest. the interiors of quark stars could replicate conditions present in the universe a fraction of a second after the Big Bang. The Methuselah star, or HD 140283, has baffled astronomers with its apparent age. Located about 190 light-years away, it is one of the oldest stars ever discovered. So old, in fact, that early estimates suggested it was older than the universe itself. How old is the Methuselah star? Initial calculations placed the star's age at 14.46 billion years, slightly older than the universe's estimated age of 13.8 billion years. This created a paradox. How could a star be older than the universe? Astronomers have since refined their models, adjusting for uncertainties in the star's distance, metallicity, and luminosity. Today, the Methuselah star's age is estimated at 13.7 billion years, just slightly younger than the universe, but still ancient enough to be a relic of the cosmos' earliest days. A star from the dawn of time. The Methuselah star is a low metallicity star, meaning it contains very few elements heavier than helium. This suggests it formed shortly after the Big Bang, before heavy elements were widely distributed by supernovae. Its chemical composition includes small amounts of lithium, a rare element produced during the Big Bang. This makes the Methuselah star an invaluable tool for studying the universe's first moments. Why the age discrepancy? The age paradox surrounding the Methuselah star highlights the challenges of measuring cosmic timescales. Factors like the star's distance, temperature, and metallicity must all be precisely accounted for, and even small errors can lead to significant discrepancies. This paradox also underscores the limits of our understanding of cosmology. Could the universe be slightly older than we think? Or could there be processes we haven't yet discovered that allow stars to appear older than they are? Cosmic wanderer. The Methuselah star is a halo star, meaning it orbits the Milky Way on a highly elliptical path. Its velocity, about 1.3 million kilometers per hour, suggests it was flung into this orbit during a gravitational interaction billions of years ago. Interesting facts. The Methuselah star has been shining for more than 90% of the universe's history. Its high velocity indicates it may have originated in a dwarf galaxy that was absorbed by the Milky Way. Thorne-Zitkow objects, TZOs, are one of the strangest theoretical phenomena in astrophysics. First proposed in 1977 by physicists Kip Thorne and Anna Zitkow, these bizarre hybrids are thought to form when a neutron star is swallowed by a red supergiant. How are TZOs formed? Imagine a binary star system where one star explodes as a supernova, leaving behind a neutron star. Over time, the neutron star spirals into its massive companion, eventually sinking into the red supergiant's core. Inside the supergiant, the neutron star disrupts normal fusion processes. Instead of producing energy in the usual way, the star begins synthesizing heavy elements through rapid neutron capture. A chemical signature. TZOs would have a unique chemical signature, with their outer layers containing unusual amounts of elements like rubidium, lithium, and molybdenum. Astronomers have identified a few red supergiants with these characteristics, but no definitive TZO has been confirmed. What would they look like? From the outside, a TZO would resemble an ordinary red supergiant like Betelgeuse. However, its core would be radically different, containing a neutron star surrounded by dense layers of exotic matter. Why are TZOs important? Thorne-Zitkow objects blur the line between stars and stellar remnants, challenging our understanding of how stars evolve and interact. If confirmed, they would represent a new type of astrophysical laboratory, offering insights into both nuclear physics and stellar dynamics. Interesting facts. Theoretical models suggest TZOs could survive for hundreds of thousands of years before collapsing. The first candidate TZO, a star named HV 2112, was identified in 2014, but its status remains unconfirmed. UY Scuti is the giant among giants. Located about 9,500 light-years away in the constellation Scutum, it is a red supergiant star so immense that if it replaced our Sun, its surface would extend beyond the orbit of Jupiter. With a radius over 1,700 times that of the Sun, UY Scuti is one of the largest stars ever discovered. How was UY Scuti discovered? In 1860, German astronomers at the Bonn Observatory first catalogued UY Scuti, though its true size wasn't recognized until much later. Modern measurements, made using advanced interferometry techniques, confirmed its colossal proportions. The star lies near the Milky Way's center, in a region densely packed with gas and dust. This makes it challenging to observe, but even through this cosmic haze, UY Scuti stands out as a beacon of superlative size. What makes it so big? UY Scuti is a red supergiant, a late stage in the life of massive stars. During this phase, the star's outer layers expand dramatically as it exhausts its nuclear fuel. However, this size comes at a cost. UY Scuti loses mass at an incredible rate, shedding billions of tons of material every year. The star is also a pulsating variable, meaning its brightness changes periodically as its outer layers expand and contract. These pulsations are common in red supergiants and provide crucial data for understanding their structure and evolution. A star on borrowed time. Stars like UY Scuti live fast and die young. Its massive size means it burns through its fuel much faster than smaller stars like our Sun. Within a few million years, a cosmic blink, it will explode in a supernova, potentially leaving behind a black hole. When this happens, the explosion could outshine entire galaxies, briefly making UY Scuti one of the brightest objects in the universe. Why it shouldn't exist. The existence of stars like UY Scuti pushes the boundaries of what we know about stellar physics. How can a star maintain such a massive, extended envelope without tearing itself apart? Researchers are still working to refine models of stellar structure to account for the extremes of red supergiants. Interesting facts. 1. If UY Scuti were placed at the center of our solar system, its surface would engulf not just Earth but Mars, Jupiter, and possibly Saturn. 2. Despite its size, UY Scuti is relatively dim because its energy is spread across such a vast surface area. Hypervelocity stars are the rebels of the galaxy. While most stars orbit their galactic centers in orderly paths, hypervelocity stars are ejected at incredible speeds, often exceeding 1,000 kilometers per second. These runaway stars are so fast that they can escape the gravitational pull of their home galaxy entirely, wandering into intergalactic space. What causes hypervelocity stars? There are two main mechanisms that can launch a star to hypervelocity speeds. 1. Black hole interactions. When a binary star system passes near a supermassive black hole, one star may be captured by the black hole's gravity, while the other is flung outward at extreme velocities. This process is thought to be the source of many hypervelocity stars in the Milky Way. 2. Supernova explosions. If a massive star in a binary system explodes as a supernova, its companion star can be hurled into space by the shock wave. Discovering the Wanderers. The first hypervelocity star, He 0437 5439, was discovered in 2005. It is speeding away from the Milky Way at over 700 kilometers per second and is currently located about 200,000 light-years from Earth. In 2021, astronomers using the Gaia Space Telescope identified dozens more hypervelocity stars, many of them on trajectories that suggest they originated near the Milky Way's center. Life as a hypervelocity star. These stars are often young, massive, and hot, with short lifespans. Once ejected, they travel through the vast emptiness of intergalactic space, where they will eventually burn out, leaving behind faint remnants. The idea of planets orbiting hypervelocity stars has also intrigued scientists. If such planets exist, they would experience the ultimate cosmic road trip, journeying across the universe at mind-boggling speeds. Interesting facts. 1. The fastest hypervelocity stars can reach speeds of 1,500 kilometers per second, enough to travel from Earth to the Moon in just 4 minutes. 2. Some hypervelocity stars may have originated in dwarf galaxies absorbed by the Milky Way, making them relics of cosmic mergers. Eta Carinae is a stellar time bomb. Located in the Carina Nebula, about 7,500 light-years from Earth, it is one of the most massive and luminous stars in the Milky Way. This binary star system has already experienced a violent outburst in the 19th century, known as the Great Eruption, during which it briefly became the second brightest star in the sky. The Great Eruption. In the 1840s, Eta Carinae underwent a massive eruption that ejected an estimated 10 times the mass of the Sun into space. This material formed the Homunculus Nebula, a pair of glowing lobes surrounding the star. Remarkably, Eta Carinae survived this catastrophic event, but it remains highly unstable. A binary system on the brink. Eta Carinae is actually a binary system, consisting of two massive stars orbiting each other. The primary star is about 100 times the mass of the Sun, while its companion is slightly smaller but equally unstable. The intense gravitational interactions between these two stars create violent outbursts of energy and material, further destabilizing the system. The impending supernova. Astronomers believe Eta Carinii is nearing the end of its life. Within the next few 100,000 years, possibly even sooner, it will explode in a supernova or hypernova. This explosion could be visible from Earth even during the daytime and might produce a gamma-ray burst, a focused jet of energy capable of impacting nearby star systems. Why it matters. Eta Carinii is a rare opportunity to study the late stages of massive star evolution. It is one of the few stars we can observe in real time as it approaches its final catastrophic moments. Interesting facts. 1. Eta Carinii emits over 5 million times the energy of the Sun, making it one of the brightest stars in the galaxy. 2. The homunculus nebula, created by the Great Eruption, continues to expand at a rate of about 1.5 million kilometers per hour. The universe is filled with wonders that challenge our understanding of existence. From impossibly large stars to stellar remnants traveling faster than light itself, these cosmic anomalies reveal the incredible diversity of the cosmos. If you enjoyed this journey through the universe's weirdest stars, don't forget to like, share, and subscribe to Infinitia Verity. Hit the notification bell to stay updated on all our future explorations. Share your thoughts in the comments. What's your favorite weird star? Until next time, keep looking up and stay curious about the infinite truths of our universe.